So this is section 11.7. We're skipping to this section as a continuation of parametric equations in our last session. So this actually makes sense to me to do this right now. There's some pretty cool pictures I think I put on the notes for you to look at. Some parametric equations that involve trigonometric functions. And you can get some really interesting graphs, things that you've never imagined being able to graph yourself. So you can look at those pictures and kind of go, ooh, that's kind of cool. So let's start with our first one. And I want you to notice on our first example here, now we have a trig function involved. So our procedure is going to be slightly different from what we did earlier. Those were the simplest kind, where no trig functions were involved, and we just solved one of the equations for t, substituted into the other equation, and eliminated the parameter in that way. This is going to be different with trig functions. Not that it's harder, it's just different. So instead of solving for the parameter theta, which I do not want you to do, when there's trig functions involved, do not solve for theta. What I want you to do instead is I want you to solve for the trig function. Get the trig function all by itself. So in the first case, with the x equation, I would divide both sides by 2 to get x over 2 as cosine theta. Likewise, on the other one, I will divide both sides by 2 to get sine of theta by itself. Now, when trig functions are involved, I'm going to ask you to think back to we're supposed to make a table of values and plot the points. Oh my gosh, that's not at all the way I really want to do this. But we're going to do it this once, just to show you that it will work. We're going to get some really nasty looking numbers. So I'll go ahead and apologize. This is not the best way in my mind to do this. So, whoops, I wrote a t, didn't I? Darn, it's supposed to be a theta. So let me get rid of that t that I wrote. I need to find a better way to undo things that I messed up. That's what I found to do so far. So, sorry, this is theta, not t. So we're going from 0 to 2 pi, so I'm going to pick some numbers for theta. In the first quadrant, I'm going to pick all of the special ones that we know a lot of stuff about. And then in other quadrants, I'm going to be a little bit more selective and not pick everything, because I'm hoping that just a little bit of information will be sufficient to get us there. So I'm just finding a few. I think by the time we get to 3 pi over 2, we're going to kind of know what's going on. So I'm getting kind of thin in values at that stage. All right, so when theta is 0, doing x's first. I'm going to do all the x's first. Cosine of 0 is 1. 2 times 1 is 2. Cosine of pi over 6 is square root of 3 over 2. Times 2 is square root of 3. Which you probably want to get a decimal value. Let me get my calculator so that I can get that with a little bit of accuracy and not have to guess as much, because I'd like for you to have a good value. So about 1.7. I think I said in the last one that was about 1.8 or 9, and I was wrong. So it is about 1.7. And I don't need a whole lot of decimals here, because there's no way I could tell the difference between graphing 1.7 and graphing 1.7320508. There's just no way that I'm going to be able to see that kind of clarity. Okay, anyway, back to the x values. Cosine of pi over 4 is square root of 2 over 2. Multiplied by 2 is square root of 2. That's 1.414. That's one of those that I actually have memorized, because I've seen it a lot. Cosine of pi over 3 is 1/2. 2 times 1/2 is 1. Cosine of pi over 2 is 0. 2 times 0 is 0. Cosine of 3 pi over 4 is negative square root of 2 over 2 times 2 is negative square root of 2. So that's going to be approximately negative 1.4. Cosine of pi is negative 1. 2 times negative 1 is negative 1. Cosine of 7 pi over 6 is negative square root of 3 over 2. Multiplied by 2 is negative square root of 3, which is about negative 1.7. You can see why I don't have to have as many values, because we're getting similar answers, but perhaps with a negative instead of a positive sign on them. So we're going to be able to use that idea. Anyway, cosine of 3 pi over 2 is 0. 2 times 0 is 0. And cosine of 2 pi is 1. 2 times 1 is 2. All right, the y values. Sine of 0 is 0 times 2 is 0. Sine of pi over 6 is 1/2 times 2 is 1. Sine of pi over 4 is square root of 2 over 2 times 2 is square root of 2, which is about 1.414. Just writing 1.4. Sine of pi over 3 is square root of 3 over 2. Square root of 3 over 2 times 2 is square root of 3. It's about 1.7. Sine of pi over 2 is 1 times 2 is 2. Sine square root of 2 over 2 times 2 is square root of 2. So that's about 1.4. Sine of pi is 0. 2 times 0 is 0. Sine of 7 pi over 6 is negative 1/2 times 2 is negative 1. Sine of 3 pi over 2 is negative 1 times 2 is negative 2. And sine of 2 pi is 0 times 2 is 0. Whew! Wow. All right, so the x's and y's aren't going beyond a value of 2 or negative 2. So when I go to graph this, I'm going to go ahead and make my x scale fairly large and my y scale also fairly large. If I want this to be a graph that's not distorted, I do want to make sure that the marks are equally spaced in both directions, so that one on the x-axis conceivably has the same length as one on the y-axis. Otherwise your graph will be distorted. Not that that's necessarily bad, but if you want to find out what it is from the graph, you really need a really good graph to do that. Okay, so 2, 0 is our first point, when theta is 0. And what I'm going to do here is I'm not going to write theta equals 0 next to this and all the other thetas, because that really crowds it up. I'm just going to kind of keep track in my mind where I started and what order I plotted them in when we're trying to get the direction of the curve. Okay, so next point is at 1.7, 1. About right there. Next point is at 1.4, 1.4, so about right there. The next point is at 1, 1.7, about right there. The next point is at 0, 2. Next point is negative 1.4, positive 1.4. Say it's about right there. Next point is at negative 1, 0. Next point is at negative 1.7, negative 1. It's about right there. Next point is at 0, negative 2, and then 2, back to 2, 0. So if you're looking at that, you may say, hey, because I'm going the same direction from what appears to me to be the center at 0, 0, I'm going 2 in the x direction and 2 in the y direction, I think this is a circle. So I'm going to plot the circle through those points I graphed. Try my best to make it look good. The beginning of that circle looked pretty bad. Sorry about that. And the direction of movement was counterclockwise. All right. So we've made a table. Then our next task is going to be to rewrite this without the parameter. So we're going to eliminate the parameter. So I'm kind of going back to where I was before. This is now what we're doing is, remember I said solve the trig function, solve for the trig function in each equation. Then looking at the two trig functions that are involved, sine of theta and cosine of theta, see if there is an identity that relates those two to each other and nothing else. So in other words, I don't want to pull in tangent of theta or anything like that. I want to stick with just sine of theta and cosine of theta. Well, I do know that there's the Pythagorean identity, cosine squared theta plus sine squared theta equals 1. So I could substitute into that identity, which is I know is true for every cosine theta, sine theta that I could have. I can substitute for cosine of theta with x over 2 squared, and substitute for sine of theta with y over 2 squared equals 1. And simplifying, I get x squared over 4 plus y squared over 4 equals 1. By the way, this is the standard form for an ellipse. And the cool thing is, with an x radius and a y radius of 2 each, that means that this ellipse is actually a circle. So when the x radius and y radius of an ellipse are equal, that gives you a circle. So just like a square is a special rectangle, a circle is a special ellipse. So it does take the form of an ellipse, but we want it in the standard form for a circle. So I'm going to multiply both sides of the equation by 4, which simplifies to be x squared. Multiplying the next thing by 4 gives me y squared, equals multiplying that by 4 gives me 4, which is a circle centered at 0 with a radius of 2, which is exactly what we graphed. And again, to get the orientation, you have to use the parametric equations. As t increases, which way is that thing moving along the path? Alrighty. So, for this next one, this is what I really wanted to do on the last one, but it had said, make a table of values, and you can see how painful that was and how much time that took. They may have written a t there. When it's trig functions, I tend to like theta, so I'm going to change the problem to be theta, but you can certainly use t. There's no problem with doing that. It won't hurt a thing. So anyway, going from 0 to 2 pi for the theta values, or I guess you could say for the t values if that's what you wanted to use. So as I said before, solve each of these equations. Because there's a trig function involved, solve for the trig function. Don't solve for the parameter theta or the parameter t if they've written it that way, but instead solve for sine of theta in the first one and cosine of theta in the second one. Again, the identity that relates those two to each other is sine squared theta plus cosine squared theta equals 1. Do you notice what I did there? I intentionally made it sine squared plus cosine squared this time, so that I would have the x thing showing up first and the y thing showing up second. If your x is related to your cosine, then you'd want to do the cosine squared plus sine squared theta equals 1 instead. So I'm kind of doing that on purpose. All right, so substituting in for sine of theta with x over 2, and substituting for cosine of theta with y over 3, we get this equation. Distributing the exponent to numerator and denominator gives me x squared over 4, plus y squared over 9, which equals 1. All right, so this is the standard form for the equation of an ellipse. The center is at 0, 0. And the x radius is 2 and the y radius is 3. So again, to try to make the scale on both axes the same distance for each one, that makes it, as much as possible, not become a distorted graph. Okay, so if I graph the entire ellipse, I might be actually graphing too much. And what I mean by that is we're only supposed to graph from 0 to 2 pi. If it said graph from negative infinity to infinity, that would definitely be the entire ellipse, unless there were something in the equation that said, nope, x can only be positive or x can only be negative, etc. So I'm going to be a little bit careful. I'm going to start by graphing the entire ellipse, and then I'm going to check to see that we actually are supposed to do the whole thing by checking some values. So the center is at 0, 0. The x radius is 2, so I'm going to graph 2 to the left and 2 to the right from the center, and the y radius is 3, so graph up 3, down 3. And then here's the entire ellipse. And I just happen to start up there because that's where I start drawing circular looking, ovally looking things. That doesn't mean it's where it actually started. That's not known yet. So we should probably know, if we were asked, well, where did it start? And to do that, you might make an abbreviated table of values. We don't want to do a whole bunch of them. As I said before, that's painful. But doing a few to get the direction of the curve, which is called the orientation of the curve as well, and where it starts and ends, that's probably a good idea. So I'm going to go 0. I could go halfway to pi, but that means a lot of times I won't know, like if I'm going all the way around the circle once, or here's an ellipse, did that mean I went clockwise or counterclockwise? So I don't want to pick pi necessarily. I want to pick something actually close to the first theta I chose is a really good idea, because that will tell you for sure what direction you're moving as theta increases. And then I'm going to find out where I am at 2 pi as well. So beginning point, ending point, and a third point that's really close to the first one so that I can determine the direction of movement. All right, so for x, sine of 0 is 0, 2 times 0 is 0. For x, sine of pi over 6 is 1/2. 1/2 times 2 is 1. And sine of 0 is 0, 2 times 0 is 0. All right. For y, cosine of 0 is 1, 3 times 1 is 3. So that means we're starting at 0, 3. Oh, I lucked out. We actually start there. This is at theta equals 0. If you want to write that in, it doesn't hurt. So cosine of pi over 6 is square root of 3 over 2. Multiplied by 3 is 3 squared roots of 3 over 2, which is, let me get my calculator and see, about 2.6. And cosine of 2 pi is 1, 3 times 1 is 3. So we actually are going to end on the same point where we started. Now, an interesting thing is, did we go around more than once? Or did we just go around the one time? So that's where, if we were to find pi and find out that we were at 0, -3 at that point, that means we go around exactly once. So I'm going to go ahead and do that one. I said I wasn't going to, now I am, sorry. So pi, sine of pi is 0, 2 times 0 is 0. Cosine of pi is -1, 3 times -1 is -3. Yeah, at pi, we're down here. So that means we're going around exactly one time. So one time around. Alrighty. So what's the direction of movement? Did we go clockwise or counterclockwise? Well, that's why we did pi over 6. Graphing that point, that ends up being 1 and about 2.6. And you can assume that that is a point on the curve. You don't have to try to graph that real exactly because you know it's a point on the curve. This is at theta equals pi over 6. So from 0 to pi over 6, we're moving clockwise around this thing. So now indicate the direction of movement, and you're done. All right, so now that we've completed that, we're going to move on to the next thing. The next item, the cycloid, is sort of interest. It's kind of like if you were driving your car or a bicycle and ran over a piece of gum and it stuck to your tire, and you could look from the side and see the path that gum takes as it goes along the circumference of the tire round and round it goes. As time goes on, like if you're watching it from the side as the car goes down the road, or the bicycle goes down the road, what would the path of that piece of gum look like? And that's what is called a cycloid. A cycloid is defined as anything that's of the form x equals at minus a sine of t. By the way, please don't get worried. This is not something I'm going to ask you to memorize. This is more in the sense or the spirit of interest, an interesting result. So this is what it would look like. And t would be all real numbers. So negative infinity to positive infinity. All right, so let's graph a specific one of these cycloids. Let's graph x equals t minus sine of t. So what is a? Right, it's 1. And so y would be 1 minus 1 cosine t, or just 1 minus cosine t. Now, as far as trying to do this analytically, because this is a mixture of the normal parametric one where you have like polynomials, that t in the x part reminds me of that, and we have the trig functions, we're not going to be able to eliminate the parameter when there's a mixture of trig functions and polynomial functions. So the only good way to do this for us is we're going to have to resolve ourselves to the fact that we're going to need to make a table of values. So we would calculate for various t values what is x and what is y. And since we've done this already a little bit, if you're okay, I'm just going to maybe do one or two with you and then just give you answers. So I think I'll do 0 and pi over 4 with you and then give you the rest of the answers as if we'd gone through them to save ourselves a little bit of time. So once you've done 2, you could actually do the others if you were in need of doing so. Let me finish out all the way to 2 pi. Okay, so when t is 0, let's do the x. 0 minus sine of 0. Since sine of 0 is 0, 0 minus 0 is 0. Pi over 4. Sine of pi over 4 is square root of 2 over 2. So this is going to be pi over 4 minus square root of 2 over 2, which I have no idea exactly where that is. So I would punch that in my calculator and get an approximation for that, and it ends up being 0.08. Sorry, I'm kind of running into the y region. So that's why I'm not going to do this that many times, because we really want the decimal for graphing purposes. Okay, so for y, cosine of 0 is 1. 1 minus 1 is 0. For y, when t is pi over 4, cosine of pi over 4 is square root of 2 over 2. That's 1 minus square root of 2 over 2, which is a decimal that's about 0.3. So if we kept doing that for all of these angles, the x's for pi over 2 will get 0.6. And you can verify maybe a couple of these and make sure that they're correct. Pi is going to be pi, which is of course 3.14. 3 pi over 2 is 5.7. And 2 pi is 2 pi, which is about 6.28. All right, when y is, what are the y values for pi over 2? That's 1. For pi, it's 2. For 3 pi over 2, it's 1. And for 2 pi, 0. All right, so the y values, the biggest I see that we get to is 2. So make that fairly large, and let's make this be about the same. So, no, let's make it a little bit smaller because we're going to have to go all the way out to 6.28. And of course, see, did they ask us to graph for negative infinity to positive infinity? No, just from 0 to 2 pi. Okay, so I probably should have written that down. So we're going to go from 0 to 2 pi and stop. Wait, did they include 2 pi? Yes, they did. So let me back up a second and make that include 2 pi. All right, so since we're going to be going out to 6.28, I'm going to make my 1 on this axis a little bit smaller than on the y-axis, which means this is definitely a distorted graph, and we know that going in. It's not terribly distorted, but it is somewhat distorted. So plotting the points, 0, 0, 0.08, 0.3, really close to the y-axis, 0.61, so 0.61 is about right there. Pi, which is 3.1412, 3.142. 5.7, 1, 2, 3, 4, 5.7, and 1. It's about right there. And 2 pi is 6.28, 1, 2, 3, 4, 5, 6.28, 0. It's about right there. And so it ends up looking like this. This is not a circle, because if we were to continue beyond 2 pi, it would then do this and do the exact same shape again, and then it would keep going like that over and over and over. That last part I did where it's really darkened a lot more is not what they ask us to graph. It stops at 2 pi at this point on the x-axis right here. That's the stopping point, and the direction of movement is along that curve. I was just showing you the other one to say that's what the cycloid looks like, is it's that hump that comes down to a sharp point and then goes back up like that, and it just repeats itself over and over and over again if you were graphing all real numbers. Okay, so next example. 3 golf balls are hit simultaneously into the air at 132 feet per second, making angles of 30 degrees, 50 degrees, and 70 degrees with the horizontal. Assuming the ground is level, determine graphically which ball travels the farthest. Estimate this distance. You know, I intended for this to be an in-class example because I was going to show you on a graphing calculator, and this was just for fun more than anything else. So unless you have a graphing calculator, you're not going to be able to get the advantage of seeing this. So I'm just going to tell you the answers and what they would be. So x sub 1 would be 132 cosine of 30 degrees t, and y sub 1 would be 132 sine of 30 degrees t minus 16t squared. X sub 2 is going to look very similar, except that the angle is different. So 132 cosine of 50 degrees t. Y sub 2 is 132 sine of 50 degrees t minus 16t squared. And x sub 3, just use our third angle, 132 cosine of 70 degrees t and y sub 3 is 132 sine of 70 degrees t minus 16t squared. And if we were to graph, as it turns out, I would show you how I could determine the window and all that, but I'm just going to show you that if we went with t on the range from 0 to 9, that would actually capture, in the graphing calculator, would capture all of these graphs. And so let's see. So let me show you what those graphs look like. If you were in a graphing calculator, this is kind of what you'd see. Let's see. Let's see which one's which. Okay, so the 50-degree one looks like this. So that's this one, okay? The one with 70 degrees looks like this. Which is this one. And the one that's 30 degrees looks like this one. Okay. And I haven't shown you any scale because it's not really necessary, because we're not actually going to be able to answer these questions that they posed without the graphing technology. But the question, one of the questions was, which one of those goes the farthest? And that would be the red graph because its horizontal distance is the greatest. So the one hit at 50 degrees, oops, I didn't color code this one. The one hit at 50 degrees goes the furthest. Okay. And you wouldn't know exactly what this is because you'd have to use your graphing calculator to find that value right there, the horizontal distance. And it ends up being about 540 feet, if you're curious to know what the answer would have been. And then the greatest height, well, that's the one that's green. So the ball hit at, that's a 70-degree one, the green one. 70 degrees goes highest. And just how high? Well, again, on the graphing calculator, that wouldn't be hard to determine. What we're looking for is how high that is. So we're looking for that y value to find out how high that is. And without a graphing calculator, we're not going to know how to do that. But if you use the graphing calculator, that ends up being about 240 feet. Okay? So so move this down. All right, so let's do another example. A small rocket's launched from a table that's 3.36 feet above the ground. Its initial velocity is 64 feet per second and is launched at an angle of 30 degrees with respect to the ground. Find the rectangular equation that models this path. What type of path does the rocket follow? Okay, so since this is projectile motion, we know that this is going to be the initial velocity multiplied by the cosine of the initial angle which it's launched, 30 degrees, times t, and y is 64 sine of 36 degrees. I'm sorry, sine of 30 degrees times t minus 16t squared plus the initial height. The original y is going to have to be coming off of 0, and so we're going to move it up 3.36 so that it begins at that height right there. And so if we simplify, cosine of 30 degrees is square root of 3 over 2 times 64 is 32 square roots of 3 t. And y will be sine of 30 degrees is 1/2 times 64 is 32t minus 16t squared plus 3.36. All right. So if we want to eliminate the parameter, this first equation with x is going to be the easiest one to eliminate the parameter with. So solving for t, we'll divide both sides by the 32 square roots of 3. And then substitute that into the other equation for each t. So that's going to be 32 times x over 32 square roots of 3 quantity squared. Oh, I'm sorry, just t, my bad. Just that. Minus 16 times x over 32 square roots of 3, this time squared, plus 3.36. And so, simplifying, we'll get x over the square root of 3, because the 32's cancel, minus 16 times x squared over, so we'll square the 32, which is 1024, and we'll square the square root of 3, which is 3, so 1024 times 3 is 3072, plus 3.36, and then to have it in a little bit more pleasing order, I'm going to put the x squared term first. The 16 and 3072 simplifies to be 1 over 192, so negative 1 over 192 x squared. And then rationalizing the x term, that'll be square root of 3 over 3 times x plus 3.36. And of course, that's the equation of a parabola with a negative leading coefficient, means it's going to open downward. All right. So that's the type of path that it follows, is a parabolic path, because that's the equation of a parabola. Okay. So, next part of this is determine the total flight time and the horizontal distance traveled by the rocket from this last example that we completed. Okay, so for the flight time, notice that y is the vertical position. It's the vertical position of the rocket. And of course, what we want to do is find out how long it's going to take before it is back on the ground, which means back on the ground, would be y equals 0. That means back on the ground. Well, maybe I shouldn't say back on the ground because it didn't start at the ground, but on the ground, I guess, is technically correct. Now, because this, I'm just sketching the idea of this. We're starting at 3.36, and then the thing's going up and down. And we want to know what time is this that it was in the air, because this is at time 0. It'll be at the starting point. What time is it when this path takes it right back or to the ground, which is, what is t equal to when y is 0? That's what we're going to need to solve. So set our parametric y equation, which was y equals negative 16t squared plus 32t plus 3.36. Set that equal to 0 and solve for t. Of course, that's not one that I think I'll be able to factor easily at all, so I'll need to use the quadratic formula. So t, the variable, will equal the opposite of b, the opposite of the coefficient of t, plus or minus the square root of b, which is 32, b squared, minus 4 times a is the coefficient of our squared variable, so negative 16, times c, which is the constant, 3.36. Make sure your vinculum goes all the way to the end of the product that we wrote up there for AC, all over 2 times a. Now this is not easy to type in your calculator and get it right, so I'd like for you to practice it. And make sure that's a negative 16 there. And once you've typed this in, once when you add and once when you subtract, you should get time negative 0.1 and t equal to approximately 2.1. Now, the negative answer doesn't make sense here, but let me tell you mathematically what that means. If we go back up to the graph I did of the projectile, if we graphed the whole parabola, it would continue down and cross through the x-axis at that point. And so negative 0.1 would be an x-intercept for that graph in its entirety. And of course this graph would also go this way mathematically. But that green stuff that I just graphed isn't part of our problem situation. So we ignore those, but I'm telling you that's where this negative 0.1 comes in mathematically. We ignore it because it is not going to answer our question. And so the flight time, therefore, is about 2.1 units of time, and in this problem that's seconds. Okay. And then what's the horizontal distance that it travels? So that was, the first question was when y is 0, what's t? Well, now that we know when that happens, the second question is asking us what's x, using the time that we just found. So x, the equation for x that we had was 32 square roots of 3 times t. So since our flight time is about 2.1 seconds, hopefully you stored that number in your calculator or it's still there. And we're going to substitute that in as a stored value. So please don't forget that. On paper, I might only write 2.1, but you should actually use the stored value in your calculator. You type that, you should get 116 0.4 units of distance, which in this problem would be feet. All right, that ends this lesson. I'll see you later.